Gruffudd from Heriot-Watt University, who is going to speak on forecasting aggregated wind power availability over extended regions.
Good morning. I hope you'll have quite a nice, simple talk to start the morning off here, talking about the title as already stated. Right, so the work is with myself in collaboration with Stan, also Idris Eckley and Rebecca Killick from Lancaster. So obviously what we're talking about here is the kind of quasi-real-time, the period after markets have closed when the transmission system operator is trying to kind of cope with the final uncertainties and forecast errors. So we're going with TSOs in that role of a balancer of last resort in the final hour. And of course, the goal of the TSO here is to make sure that the risk of having an insufficient generation is kept acceptably low, and trying to find that optimum balance, of course, between cost and risk. And with increasing amounts of renewable energy, then finding that balance needs more dynamic, probabilistic approaches for each hour. So a Bayesian approach is obviously quite a natural choice here, giving you your posterior predictive probability distributions, so that you can kind of find that optimum, as Pierre was talking yesterday about the need for that full information about your probability distributions in order to come up with your truly optimal solutions. And typically wind farms for an operator will be scattered over quite an extensive area, such as a country maybe, and in that situation then the wind resource can't be well characterized by a single speed, rather a vector of representative speeds. And of course your distribution for the aggregate power can then be derived from the joint distribution of those individual wind speeds. So given how complex and dynamic the spatial temporal structures are associated with those wind speeds, it seems natural that you would require some kind of adaptive multivariate model in order to try to capture the evolution of this process. So if I was representing the random process for the aggregate power by lambda and its values by a small lambda, and then also of course t is the time and s is the forecast horizon. And here we're really thinking about that forecast horizon being 1 and 2 hours ahead. And then of course it's important that as a multivariate model that we have the full field of information of past values and so on that are relevant to that distribution. And if we have such a complete set of information, then the predictions will be devoid of any kind of spatial structure. And if there is any, sorry, I meant temporal structure. And if there is any temporal structure, obviously that's an indication that we're not making full use of the information that's available. So I've taken a graphic here, actually out of a master's thesis, but it's quite widely reproduced, kind of showing that as you're going towards the very smallest number of hours, then time series models do give you smaller errors than meteorological forecasts. So that's another motivation why forecasting would be based on statistical models in that time period, of course, in addition to that need for the full distribution. Now, because the effective power curve for a zone, it's not a monotonic function. There's a softening towards the cutoff at the top and so on. So that means that a power output, it doesn't really represent that full set of information. So really what's of interest when working out the joint distribution is the wind speeds rather than the wind powers, and then conversion to powers happens at a later stage. 2-1. Sorry. Okay, yes. So a natural choice of model would be the dynamic linear model. And this is a very kind of natural and a powerful framework for modeling these kind of zonal wind speeds. And it's also quite novel to apply this type of model towards wind. And a kind of gradual process of increasing sophistication is necessary. So yes, considering a case of m dimensions of the wind speed, of the area is divided into m zones, and so the random number representing the power from that particular zone is then a product of the capacity in that zone, the wind speed, and of course a function as an effective power curve for that hour. Of course, that's again a dynamic function, but we assume that the TSO would then have experience and meteorological information that would enable it to have a pretty good idea of what those curves would be at a given time. Dynamic linear models assume Gaussian errors, so some kind of transformation would be necessary, and also in order to render those errors into independent standard normals, you'd have to pre-multiply with a matrix derived from the covariance matrix at that which is evolving in time. So again, so of course it's very necessary that covariance matrix does evolve to reflect the changes that are happening under different weather conditions. And not only is the covariance matrix changing in terms of the variances, but also the kind of the correlation matrix itself would realistically be changing as well. And then if somebody was working out the aggregate power, that would simply be a convolution where for a given values of all but one standardized wind speeds, you'd then kind of calculate based on theta your set of functions and parameters. And in reality, of course, one would probably do that through simulation rather than a numerical integration. And of course, in reality, they won't truly be independent, even if they have a zero linear correlation. So it then might be the case that some kind of copular function would be necessary, or maybe some kind of structure of copulars. And of course, it would also be realistic that they would be leptokurtic rather than truly normal. So just to explain the basic structure of a dynamic linear model, in case anybody's not familiar, one has the concept of a latent process and an observable process, Y, and then these are connected through the matrices F and G, and then have independent error vectors V and W. And this is a very flexible framework because one can develop separate models for separate aspects, such as seasonality, linear trends, and autoregression. And then the final observable series is the sum of processes captured by each of those models. And then also the predictive distributions are calculated through a Kalman filter, which and this is just kind of showing you that process of how one initially forms predictive distributions for your latent process. On the basis of that, then you have your predictive distributions for the observable process, and then filter backwards to once the new set of information has arrived to get some estimates of your latent process. Now, in our case, we looked at the wind speeds at 20 zones. And this is pretty much based on the 7-year system division of Great Britain into 17 zones by the national grid, with a few extra in Scotland because of the interest of area from a wind point of view. And I had a 20-year period for each of those zones, hourly average data, also wind speeds and also wind direction was obtained. So of course, even with what seems like a fairly modest number of zones in a way for an area the size of the UK, this does give you a very large number of parameters. So even a simple autoregressive moving average model of order 3-1 will give you 1,600 variables. It's not necessarily a big problem because you have 3.5 million data points for that 20-hour period. But perhaps it's more sensible to kind of consider only maybe 4 neighbors to be informative rather than making it a 20-dimensional model. So I looked at trying to fit an example of a DLM that might be suitable, at least as an initial attempt. And in this case, your matrix FT at a given time is basically your set of recent values. And the latent process is the regression coefficients, and that's assumed to be following a random walk. And for simplicity here, we assume that error covariances are constant. So after fitting such a model to several zones, I found that it yielded very small values for the random walk noise. And indeed, the Kalman filters kind of yielded changes of no more than about 1 or 2% for those regression coefficients over the course of a year, which is, of course, is definitely kind of smaller than we know for a fact that from kind of day to day, realistically, those kind of regression coefficients would change more significantly. I also found interestingly that if you compared just a static model to that dynamic one, the error variance is only reduced by a very small number, about 0.1%. Also found that a third order model and a first order one were only different by under 2%, which is again kind of quite a surprisingly small difference, really. So this is kind of seems to be suggesting that actually adding sophistication to these kind of models isn't actually delivering the kind of improvements that one would really be, intuitively expect. So I fitted univariate. So the idea then is that since these kind of more sophisticated ones weren't behaving maybe as was anticipated, that it might be a good idea to go back and try to kind of start with the most simple models and kind of build up gradually in a more layered approach. So I just fitted univariate ARMA models to a random selection of 4 of those zones. So I found that the model that gave me the smallest error variance was my ARMA 2-1 in most cases, with ARMA 3 in 1. However, if I was looking at the kind of percentiles, my extreme values, actually the very simplest models actually gave the best results. Also, it turned out that even the very simple AR1 model, which essentially is just the persistence model in this context, was actually able to remove the majority of a spatial, a temporal structure in the majority of cases, or certainly an AR2 could do in all cases. Then looking at the spatial structure, I've got obviously with 20 zones, the number of pairs was fairly high. So I plotted here some histograms of what those error covariances were. So we see that most of them were kind of in the range between 0.05 and 0.1. So the one on the left here is for the AR1 model, and then the other one for the more complex ARMA 2-1. I'll actually see that there's been some kind of a small reducing in those, and a reduction of the larger values, but it doesn't really. The effect was still quite subtle. So even using univariate models, making them more sophisticated, does have some impact on reducing the spatial structure, but it's a pretty small effect. But then I considered, well, even though most of them are below a value of 0.1, what is their combined effect? So I used those matrices to calculate what would be the standard deviation of the aggregated error, and then divide that by what would it be if those errors were entirely independent. And so you see that actually they do have some accumulated effect, giving ratios of about 1.51, 1.46 there. It is definitely meaningful, those patterns, and slightly reduced, but not by a great amount. Then I kind of looked at in more detail at a cluster of neighbouring zones, 4, 6, 7, and 8, and looked at what kind of structure do you have. I'll have a diagram coming up in the next slide, and finding, as one might expect, of course, that peak in the correlation is shifted by a few hours and remains significant for about 5 or 6 hours, and kind of moving from the very simplest model to slightly more sophisticated, kept the shape, but kind of had and to just reduce those correlations by a small percentage. And then I kind of thought, well, can I try to capture what the covariance is just by looking at a small sample and moving that kind of window along through the larger sample, to see whether we could see some kind of pattern of maybe over the course of a week, maybe the dependency on kind of downwind sites increasing and decreasing maybe with a pattern, but that wasn't the case at all. It just looked purely like white noise, and the variance was, as you'd expected, just from if the correlation values truly were stationary. Then concentrating just on a pair of sites, and what was of interest to me then was under what conditions and how often does an upwind site improve the skill of a very simple forecast for those AR1 or AR3 models. And in this case, those sites were separated by about 123 kilometers, and was kind of reasonably well aligned to the prevailing wind direction in the UK. And this is just showing your cross-correlation function, showing that there is a slight shift from 0, representing the fact that they do have that relationship to each other. And the time series plot does show that in general, periods of windiness do happen more or less at the same time, but there is some difference. Actually, in this section, it was the opposite to the more average pattern, where the downwind sites was mainly leading, which does happen. So this is a cross-correlogram of errors, initially just for easing the persistence model, and then the other one, the vector ALMA 2.1. So we see that they did remove a significant amount of the main temporal structure for the smallest lags, but actually made slightly worse lags within that sort of 10 to 20 and minus 10 to minus 20 hours. And so these are the coefficient values for those types of model, kind of starting with the simplest. For the two, the first one is zone 7 using zone 8 as informative, and then the second one the reverse. So the amount the extent to which the other site is informative is fairly small. Obviously, slightly greater in the case of one is down upwind to the other. But actually, the error variance was only reduced by a very small, about 1.31%, moving from the very simplest to those more sophisticated and multivariate model. Actually, 1.31% in the one and slightly bigger on the other, but still not a huge amount, actually. And also, it was found that using that the information from the two sites only added skill to your forecasts 52.6% of the time. So I was quite surprised that it wasn't able to improve it more often. But fortunately, using the multivariate model does provide help when you need it most, in a sense. That is when the errors are at their greatest. So if you're looking at the kind of the first 5 percentiles, the most extreme negative changes, then the model does perform kind of better for a slightly higher percentage of the time, 55.7, and for the largest positive changes, then it's nearly 70%. So that's slightly encouraging. But actually, for the smallest errors, between the 40th and the 60 percentiles, it was actually unhelpful most of the time. It only added skill 34% of the time. And when you're looking at the similar between just using one site and two, with order 3, you had a pretty similar statistic. And I looked at days in an example month and said, well, how many hours within that day was the model using 2 locations more skillful than the most simple one? And of course, this ranged from 20 to about 4, even from one day to the next. So clearly, this is a situation that's evolving quite quickly. And if you had a DLM which is kind of slowly learning whether the other site is informative or not, clearly that would be too slow to cope with this kind of situation. By the time it had kind of learnt that at the moment this other site is useful, it seems that the dynamics of the situation would have changed, and that would be no longer the case. What's that? Oh yes. Oh yes. So I kind of, out of interest, kind of repeated, fitted a model only to those largest and most extreme of errors, and contrasted it to a model fitted to the smallest of errors. That's not something that you could actually do in practice, of course, because it relies on knowing what those errors were before you fitting it. But it did seem that if you were able to sort of guess in another way how big that error is likely to be, then of course you could fit separate models for those conditions. And in this case, it does have a more significant effect. But by fitting a separate model for those largest errors, that reduced your variance by about 10%, which is of course significantly better than about 3.5 as it was previously. Also, I considered whether instead of regressing on the speed at the location, I thought maybe why not regressing on how much the speed changed in the previous hour, and this led to actually slightly better results and also more consistent. For all kind of quantile segments that I looked at, actually this model proved more skillful than persistence throughout. But for the largest changes, the percentage of hours where it was more skillful was considerably less than from the previous model. So it's showing that in reality it would be very useful to kind of if one had a good set of meteorological information about what's likely to be happening, then that would kind of tell you what model structure would be the best to be used in that hour, and it's not at all obvious. I think that's just so by fitting models in a different way, it's the fact that it performs better for the most extreme errors isn't just an artifact of the fact that you're fitting using mean errors. It's just the case that for that percentage of hours, the other zone is kind of nudging you in a certain direction, and obviously that direction is correct or not depends on quite complicated dynamics rather than just. And yes, I think I can skip this one. So just to check, in case this was just a fluke for the two zones that I looked at, I considered another pair of zones with a similar level of separation. In this case, the shift in temporal structure from zero lag was a little bit more pronounced, and in fact, it seemed that the neighbour was a bit more informative, but the difference wasn't huge. And again, you're seeing a similar level of percentage of hours where the neighbour was informative in here, 52%. So it seems that conclusion was hopefully quite general. So now, looking at wind direction, here you can see that actually, even though there is a prevailing wind, it wasn't very clear. Well, in the case of Zone 8, the prevailing wind was there's two kind of main directions. Though for some reason, in the case of Zone 7, it wasn't particularly dominated by any one direction. So I looked then at kind of binning my errors variance according to 10-degree segments in which the data came in. So it's obvious that when coming from direction about 180, obviously you are getting much bigger errors than in other directions. And actually, this plot is showing the two models, the one just using a single site and another one using two, and you can barely make out the difference between the lines because their performance is so close. And also the second graph here is showing that the percentage of hours where they outperform, and it's pretty flat looking, and it's even flatter if you're using the direction at the upwind sites as for conditioning, particularly when you're looking at the number of how often it outperforms. It's a very flat graph indeed. Slightly more relevant is the difference in angle between those two sites. Not a great deal. So obviously, when here because of the rareness of it, any difference greater than 90 or minus 90, I've been into one category. So yeah, it does. It's obviously when those differences are very large, you're kind of seeing about 40% of hours where that neighbour was informative, in contrast to about 60% when they're pretty much in the same direction. So this is a more useful way than fitting separate models for different directions. So the message seems to be that obviously we do need to be using statistical models in order to have that full distribution and so on, and to know exactly what's going on and to be able to optimize. But it seems unlikely that a kind of slowly evolving and learning model might be the way forward, because that learning is too slow. And even if you know, even when the wind is coming exactly in the direction in which those two locations are aligned, even in that case, then that site is only helpful in about 60% of cases. So it would seem that one would have to make use of a very detailed meteorological information to determine what type of model structure would be most useful during a given hour. And that's my talk.
Right, any questions?
Slightly surprising that the use of the spatial information isn't more useful.
Yeah.
And I was wondering why that is. Whether there's some intrinsic chaos in the system that you can probably do very little about. And even with fairly simple models, you've taken out most of what you can do.
Yeah.
On the other hand, what argues a little bit against that is the fact that we still seem to have correlations and errors between sites
Exactly.
that are fairly close to each other, which you wouldn't expect if it was entirely noise. I find this a little strange. I think you may be right that you need models that are more rapidly reactive. So it sounds like The message I have get is that from statistical approaches, there is a limit to what you can do. And what we really need is to use meteorological models to get the basic structure of what's going on
Yes.
in the atmosphere, and then statistical models to refine the details, local variation. And the combination of the two is probably going to be what we need.
Yes. So finding that combination is the work of the next couple of months.
Andrew.
Hi, I designed a lot of the models that National Grid used to do this, and I don't know. We at the moment are trying to extract all we can from very simple meteorological models. That's what we use, because we feel there's still some juice to be wrung out of the lemon. And it might be worth mentioning that when I saw your graph from the master's thesis of sort of wind forecast errors, to use politician speak, I didn't recognise those graphs. We expect in wintertime, in summertime when conditions are milder, to be getting a mean absolute error 24 hours ahead of 3.8%, and in wintertime when it's more choppy, it's around about 5.8%. So I don't know if that's sort of
for your whole portfolio for the whole country.
That's for the aggregated portfolio.
Yeah.
So is this affecting that crossover point, do you think, when the meteorological model becomes more effective?
Yeah.
Yeah, I mean, there's a big difference. Andrew's point, I mean, aggregate. Well, he's obviously going to do very much better with aggregate forecasts.
Yeah.
But this is very much looking at what's happening at individual locations and can we improve on that.
So that cross point, does that? Do you think that kind of supports that argument that you just have that the meteorological is more?
I think the cross point is probably somewhere round about, but it's at the point where there is going to be no further improvement in any meteorological forecast. They've already got it wrong. Rerunning the model takes 6 hours, and even if they reran the model, they probably get the same result. It's just wrong today.
Yeah.
In which case, any form of sophisticated statistical model that's based on something like a dynamic linear model or even just a time series approach is going to improve on what we do. But my gut feeling is that the time scale over which this improvement is going to occur is probably about 12 hours. Still very important, but it's not going to help us at, I don't think, at 2 days or even 1 day.
Yeah.
Hey, David.
Yeah, sorry, I was just a point of clarification. I was trying to work out what lead time you're actually forecasting for and evaluating for with this.
Well, these just the very last minute changes, just 1 or 2 hours, pretty much.
So it's 1 or 2 hours ahead.
Yeah.
Right.
That kind of point when the market has kind of announced its positions and everything, and it's all a case of making everything balance.
I was wondering, could you say a bit about benchmarking? Because obviously it depends very much geographically and meteorologically where we're taking the data from and where you're analysing. If you compared this to, say, similar efforts in other countries where there's a stronger prevailing wind, are they very far away from this? The second point is that intuitively this seems very disappointing, this result. Intuitively, if things upwind are getting windier, you kind of expect that we're going to be feeling that downwind. And I wonder if it's not the point that you need to have a model which is hierarchical, or so that when we've got certain weather patterns, we've got a model that is very, very good for that kind of weather pattern. And when we've got other kind of regional weather patterns, we know those are harder to forecast, and we shouldn't allow that data to pollute the good ones. And you're going to have to get to a position where there are weather patterns where you know the forecasts are very good and you can work very hard on those, and other weather patterns where it's just bad and it's going to remain bad, and downstream the analysts have to treat it as bad.
Yeah, I think so. I hope so. It's just kind of interesting that, you know, even when they're pretty much aligned, that you still only have that, you know, that it's barely only performing for the majority of times. And
Yeah, she was very
but it's
disappointed.
still, yeah, it's disappointing, but your approach still has to be the best one. As you say, it's just counterintuitive that it wouldn't it has to be judged more on an hour-by-hour basis. Just kind of knowing the direction might not be enough. I suppose, as Andrew was saying, it's more about kind of actually looking at what's actually happening on the ground and then saying, okay, we'll apply this model for this hour then, probably based on experience, rather than that there's no automatic procedure then for kind of picking it out maybe.
What about benchmarking? Can you compare this to results in other countries?
Not directly. Other studies that were kind of using meteorological forecasts and then trying to remove the spatio-temporal structure afterwards. I think that there's one example that we're kind of trying to model the error as a wave propagating across the country. I think in Denmark, and using that kind of model was able to kind of reduce those forecast errors by up to about 34%, I think, but only in quite favourable conditions. It was less than that in other ones, and of course our more complicated terrain, I think, is reducing your ability to do that.
Yeah, I would just like to mention that when we did this work in Denmark, it's this picture I showed yesterday, these aggregated zones, and I mean, we have the chance. Denmark is quite small, quite homogeneous terrain, and so when you have a front passing, it's much more of a rigid motion that cross the country.
Yeah.
That makes it easier, and yeah, we could see the best results were for the east coast, because prevailing wind is from the west, and so then you get all the sensors on the west coast, and you get your benefits on the east coast. But obviously the west coast is more windy, so that's where you have the most wind farms. So actually at the end, I mean, you get most of your benefits at places where you have the least turbines.
Yeah, indeed.
But in general, yeah, I have to say Denmark had much nicer results, but it's not a fair benchmark, because when you see the size of the country and the kind of wind condition you have in the UK and the homogeneity in space of the wind climate, it's not really comparable.
Exactly. So I think it's quite new to do it for us, because I suppose most of the places where this kind of study has been done before have been more like Denmark, and maybe, I don't know, Germany in general, kind of slightly flatter, rather than the north anyway, isn't it? So hopefully it's adding something to
Germany has different kind of wind climate, though. What's happening in the north and in the south is quite different. So, but yeah, the other point that was mentioned, it's about these hierarchical models or regime switching models. I mean, we could see that you have benefits in trying to sort it out, and it's very difficult to, based on expert guesses or models, decide which patterns are going to drive different type of dynamics. But there are still ways to say there's a hidden regime sequence, and you can just infer from data. So you have this kind of hidden Markov model, or Markov switching model, that's kind of permitting to combine dynamics, and that you end up with a kind of mixing of models that Yannick was mentioning yesterday. And you get quite a little improvement with that, and especially in terms of fully capturing the predictive densities. I mean, you have much better information about the varying uncertainties of your forecast.
So I guess the message is there's lots of work to be done.
Yeah, there is.
One more quick one.
I was say, I think we need to be a bit careful about this, sort of seeing or changing wind upstream and then expect to see the same thing downstream. I don't think it works like that. It depends on exactly what we're talking about. The part that's predictable in weather forecasting models in general is the motion of the large-scale systems. That's the bit they do very well at. The bit where the regime switching might be helpful is, you know, some weather types may be prone to lots of small-scale turbulence, whereas others it's dominated by the large-scale phenomena that's doing the work. And I think the challenge is to link between the weather models that do these large-scale things very well to the smaller scale, the hour-to-hour, minute-to-minute variability, and I think that's the challenge. But whether that has to be done, whether there's some predictive skill there, or whether it's just chaotic noise, I don't have a feel for. But that's where I think the challenge is.
Hopefully I can answer you next year.
Yeah, no, just very quickly, over the last period, we've been trying to see if weather radar data could not help for this kind of timescales and this kind of problem. because I mean we've been trying to catch as much as possible out of this meteorological forecast, out of the data we have from this local station, say, and I mean we need a bigger picture that would be high resolution in space and in time. And even though weather radar is very special information that's in there, that's maybe not so easy to use. I mean that could also be a next step. So you should ask. I don't know. We should give some weather radar images, but you could try to get something out of that.
Okay, so thank Griff again.